Okay, now we're ready to start talking about specific types of metamorphic rocks. So we're going to begin with the regional metamorphic rocks, which is up at the top of that chart right there. So in regional metamorphism, the agents that are going to be acting on the original rocks, which are called the protoliths, is going to be heat and directed stress. So that means that the force is coming from a particular direction. So for example, a conglomerate can be turned into a meta-conglomerate. So it's still going to be made of the same pebbles, but instead of having pebbles that are rounded like this, now the pebbles are going to be stretched like this. And so that's going to be caused by, let's say that there was a force that was being applied like this, then it turned it into that. Okay, you could, another example of this would be shale, which is a sedimentary rock, and it could be first turned into slate under low heat, but then under higher conditions of pressure and temperature, it then can turn into phyllite. And then under higher pressures and temperatures, it turns into a schist. And then finally, it turns into a gneiss. So a gneiss is considered a high-grade metamorphic rock. Forms under conditions of very high pressures and temperatures. Claystone, which is another sedimentary rock, will do the same thing when you apply heat and pressure to it. Okay, what would happen though to a igneous rock like granite and rhyolite? So granite and rhyolite, when you apply heat and pressure to them, they turn into a schist and then they turn into a gneiss. What about a intermediate type rock like diorite and gabbro? Well, they first are going to turn into greenstone and then amphibolite and then gneiss. So I would not worry about the greenstone and the amphibolite. Amphibolite has amphibole inside of it, for example. But you should notice that the end product of extreme metamorphism, regional metamorphism, is going to be gneiss. And in a gneiss, you're going to have bands of minerals. So in a schist, you're going to have minerals. So let's say that this is a particular kind of mineral, and then this is another kind of mineral. Well, you're going to have a jumble of different kinds of minerals in a schist, but they're all oriented like this. So the pressure was being applied like this, and you can see that it caused them to change their orientation. Now the difference between a schist and a gneiss, so over here in a gneiss, you're going to have a band that only consists of one kind of mineral, and then underneath it, you're going to have another band that consists of another different mineral. And then underneath that, again, we go back to that same kind of mineral again. So it makes bands of different kinds of minerals. Whereas with this, they're all just kind of lumped together. So this is going to be a high-grade metamorphism, and then this one over here would be a lower-grade metamorphism. Okay, now let's talk about contact metamorphism. So notice that this time it's only heat that is going to be causing the metamorphism. So there's not going to be any directed pressure acting on it, no directed stress, and so therefore there's not going to be foliation. So notice that these contact metamorphic rocks have no foliation. So the regional ones did, but the contact ones don't. So how can you make contact metamorphism? So what you're going to have is, let's say that it was limestone. So originally you had some limestone, and then let's say that there was a magma chamber. So magma made a chamber in here, and we know that magma is very hot. So that magma is going to alter the limestone that is surrounding the magma chamber. And that limestone changes into marble. So limestone changes to marble. Marble's the metamorphic rock. Limestone is the protolith. Sandstone is made of quartz. So if sandstone, let's say it's a sandstone that is surrounding a magma chamber, the sandstone will metamorphosize into quartzite. And then basically any other kind of rock, if it is contact metamorphosized, we refer to it as a hornfels when that happens. Okay, let's talk about hydrothermal metamorphism. So hydro means water, thermal means heat. So it's going to be when hot fluids go through the protolith, it's going to alter the minerals in the protolith. So, for example, an ultramafic rock like periodotite is out in the middle of the ocean, and let's say at a mid-ocean ridge where the plates are being pulled apart, we know that hot material from the asthenosphere is coming up at that mid-ocean ridge. Well, we also know in the ocean there's water. So that water gets heated up by that magma. It percolates through the ultramafic rocks, and then it turns them into serpentinite. And so that is going to be an example of hydrothermic. Now, it doesn't have to be water. Sometimes it can be carbon dioxide that is going through the rock and can alter it. But we're just going to stick with what water can do. Okay, then you've got burial metamorphism. So burial means it's under the ground. So an example of this is what's going to happen first to peat. So you start with the protoliths would be trees. They're not rocks, but they're the thing that turns into the metamorphic rock. One of those trees falls into the swamp, another tree falls on top of it, it gets buried. And so the pressure and also heat metamorphosizes that plant material and turns it first into peat, and then the peat turns into lignite coal, and then the lignite coal turns into anthracite coal. So remember that peat is a sedimentary rock. Lignite and bituminous coal are also a sedimentary rock. Anthracite coal is the metamorphic rock. One way of identifying anthracite coal is look at it. Do you see it's shiny? So the more the coal becomes metamorphosized, the shinier it gets. Okay, then you can have fault metamorphism. So you can take any kind of a rock and subject it to heat and directed stress, so directed forces, and it can turn into a fault breccia. So obviously this is going to occur in a fault. So let's say that you've got a rock like this, and then there's an earthquake or something, and so here's the fault that separates this rock from this rock over here. Well, let's say, just for the sake of argument, that this rock is moving in this direction, and then these rocks are moving in this direction. Well, the rocks that are in between, in here, they get smashed. They get crushed by these other rocks that are moving past them. So that's what a fault breccia is going to be. So at the surface, so up here, where it's not so hot, you have the fault breccia where it's angular pieces of rock. But down here, where it's hotter, it partially melts a little bit. And so that's where you get your myelinite from, so that the rocks get stretched out kind of like taffy. And so your myelinites would be down here, but the fault breccias would be up here towards the surface where it's not so hot. And then the last kind of metamorphism is impact metamorphism. And in this case, you would start with any kind of rock, and then it gets whacked by an asteroid. So an asteroid comes in, it hits the ground, and it's going to send pieces of rock flying through the air. And so those pieces of rock are going to be under high pressures and high temperatures, and they can be metamorphosized into what's called a tektite. All right, what happens when a metamorphic rock is heated up too much? So we know that if it's really heated up too much, it melts. And then when it solidifies, it would be an igneous rock. Can you see me? Okay, I hope you can. So in a migmatite, what happens is it partially melts. So it's not a metamorphic, because a metamorphic rock does not melt. It's not an igneous rock because it would completely melt. So it's kind of half and half. And so that's what a migmatite is going to be. All right, let's take a break, and when we come back, we'll talk about where do you find these various types of metamorphism.